Okay. Hello, everyone. My name is Tijana. I'm a PhD student at the University of Washington.
And I'm Andrés Garced. As a quick aside, I'm actually looking for PhD positions right now, so if you're looking for any students, feel free to talk to me after the talk.
And today, we're going to talk about a derivation visualization for context-free grammars. This is joint work with Morazán from Seton Hall University.
Context-free grammars are widely used to describe the syntax of modern-day programming languages, and thus students are expected to learn how to design and implement these grammars. This is an example of one such grammar. Oh, goodness. You can see on the left here, and it's written in the typical notation that you'll find in most flat textbooks today. Students are also expected to learn how to derive words in the languages of these grammars, and you can see one such example of this derivation on the right. Flat courses teach students how to do a variety of different things with context-free grammars, but our contribution today is going to be focused on the highlighted points here, designing, implementing, validating, and verifying grammars, and deriving words in the language of these grammars. Students struggle with context-free grammars for a variety of different reasons. One is that they don't know which production rule to apply when deriving a particular word, and the reason for this is that there's nothing inherent in the definition of a context-free grammar that helps them decide which rule to apply, and thus some students might think that all the rules ought to be applied. Another issue is that some students have been trained solely in deterministic programming and thus don't yet see the relevance of nondeterminism in their CS education. And finally, word derivation is inherently recursive, and some students are uncomfortable with recursion, and thus developing recursive sets of production rules. Our contribution today is a new tool to visualize grammar derivation that includes facilities to visually validate invariants of that grammar. And we would like to address the following research questions. Does the visualization tool help students better understand word derivation, their understanding of nondeterminism? Does it help with the development of correctness proofs? And does it help them with the debugging process? Thus far, we've been helping students design and implement grammars in FSM. FSM is a domain-specific language embedded in Racket, where students can implement, validate, and verify grammars and machines. Nondeterminism is a built-in feature, so students don't have to implement it themselves. And because it's a programming language, they can write unit tests to get immediate feedback on their designs, thus lessening the burden of questions on their professors and teaching assistants. It's also tightly coupled with the design recipe. These were pioneered by Felizen and others for the Intro to Program Design classroom and has been extended for context-free grammars by Morazán. To give you an idea of what this would look like in FSM, here we have the grammar that you can typically find in a flat textbook on the left, and the equivalent in FSM. So we have the constructor make CFG, and it takes as input non-terminals, terminals, production rules, and a starting non-terminal. Here we can see the design recipe for context-free grammars, and at a high level, what we'll have the students do is pick a meaningful name for their grammar, define syntactic categories for each of the languages and sub-languages needed for this grammar, to develop production rules based upon those syntactic categories, and to write unit tests for it, finish implementing it and validate their design by running those tests, and to verify their grammar through the use of invariants. This is what it looks like to implement the first 6 steps of the design recipe. You can see at the top we have the language defined in the comments, and below that the syntactic categories. So because S is a starting non-terminal, its syntactic category is the language that we're designing for, and because there's 2 sub-languages in that language, we associate a non-terminal with each of those, A to the M, B to the N, and C to the M, D to the M in this case. You can also see the constructor below that, and some unit tests at the very bottom. Here there's 2 types of unit tests, one for check derive and check not derive. They both take as input a grammar and an arbitrary number of words, and in the case of check derive, it validates that those words are in the language, and for check not derive, that they are not in the language.
So it would be a result of step 7 of the design recipe, and I would like you to pay attention to this one because we are going to be mentioning it later in the talk. So in step 7, students are required to develop invariant predicates for each syntactic category. This is an example of one such invariant predicate. So the predicate just takes as input, okay, I have to point that way, takes as input a word and returns true if the given word is in the language that the syntactic category represents. So in the case of E invariant, it would be A to the N, B to the N. And the only thing this code does is takes all the A's from the beginning of the word, takes the B's that follow, appends them and check if they're equal to the word, and compares the lengths of A's and B's. And we can also use unit testing to test these invariant predicates with different words to validate that they've written them correctly. So we can write invariant predicates for A and for F invariant, for S and F invariant, I'm sorry. So when it comes to designing and systematically approaching designing grammars, FSM does provide students with some useful features. But when it comes to word derivation itself, so far, FSM has only provided them with this observer called grammar derive, which takes as input a grammar and a word, and it just returns the leftmost derivation of that word, of that grammar, just written in the standard textbook notation. And this is kind of hard to read. If you're dealing with a larger word, you would have to kind of trace manually where each non-terminal gets substituted, and it gets very messy very quickly, especially if you're a beginner. So our contribution for today addresses this issue. It's a visualization tool that performs a stepwise derivation, and it has an option to visualize invariant predicates. This supports leftmost, rightmost, bi-level left, and bi-level right derivation. And instead of just talking about the tool, I'm just going to show you what it looks like and how you can use it for debugging. So let's see if I know how to do this. Perfect. Okay. So can you see this? Okay. So this is the grammar that you've just seen for the language A to the N, B to the N, C to the M, D to the M, just as it was written in the slides. And we're going to run the visualization with the grammar and the word AA, BB, triple C, triple D. So once we run the tool, this is what we get. So every FSM tool consists of three main components. The main visualization graphic, in this case, it's just going to be the derivation tree. Informative messages, which provide additional context on what's happening in the main visualization graphic, the last step taken. And finally, the instructions that we can click on or just execute on the keyboard that drive visualization forwards, backwards, and have zooming and dragging capabilities. So let's move the visualization one step forward. Once we do that, a single production rule is applied, and we have an informative message telling us the last rule used. It is color-coded to match the main visualization graphic, and as you might see if I step forward a few times, only the last production rule applied gets color-coded so students can immediately see on the graphic where the derivation tree extended. We have an informative message for the word that we are trying to derive and the current yield of the derivation tree, so we can see how the yield changes into the word that we're trying to derive, and eventually, once they match up, we know that the derivation is concluded. So this is what the tool looks like, but now I'm going to show you something cooler, which is how to use it for debugging. So this is a buggy grammar written by a student for the language A to the I, B to the J, C to the K, where I equals J or J equals K. So you can see here two error messages. If we run it again, same ones are going to show up. If we click on the X's, we can see exactly which words errored out, and we can see a step of the design recipe that hasn't been successfully completed. So these are special error messages called recipe-based errors that refer you to the step that you might have done wrongly. So step 6 is just run the test, see if everything runs, and redesign if necessary. So we can see here that this grammar derives the following words that are placed in check not derived, so they shouldn't be derived by the grammar. So to debug this, we can run the visualization tool with the word, say, BBBCCCAA, and we can give it as input the invariant predicates that the students have written in the step 7, so they know or they can see where the bug is. So if I go here and run this with the word, we can see, starting non-terminal, we get this new message that tells us all invariants hold because we haven't yet executed any production rules. But if we move forward, we see that the S invariant doesn't hold. So just based off of this, we don't have a lot of context about why S invariant might not hold, because S invariant should just produce the words in the language. But if we find the bottommost red node, maybe that would tell us where the bug is. So if we keep stepping, we can see that the B invariant also doesn't hold, but the E invariant holds. So presuming that the invariant predicates are written and tested correctly, now we know that E generates what it's supposed to. And even if we keep stepping through, everything is fine on the left-hand side of the tree. F invariant also seems to hold, so presuming that the invariant predicate is written correctly, F is generating what it's supposed to. So the bug could be somewhere in the B invariant. So let's move this for a second and go back to our grammar. So the bug says that it's somewhere in the B invariant. The B invariant is supposed to generate words in A to the I, B to the K, C to the K. And the production rule for B says that it generates a concatenation of E and F. Now, we know that E and F both hold, so let's see what they actually generate. So E generates B to the K, C to the K, and concatenated to that would be F with A to the I. And this doesn't match up what the B invariant should be generating. It seems like they mixed it up. So if we go back to the rule for B and correct it to FE instead of EF and run this, it seems like we've solved the bug, but let's check with the visualization. Doesn't even run because the word is not in the language of the grammar. So that's a good sign. Now, we still have one more error message, which is telling us that this word is being derived, that apparently shouldn't be derived. So let's run the visualization tool with that word. If we just click here, it's going to tell us exactly where it is. So we're just going to replace it and give invariant predicates as input. So once we run this, I'm just going to complete the tree in one step so we can immediately see where the bug is. All of the invariants seem to hold. So S generates words in the language, so seemingly this word AA, BB, CC is in the language. So if we look back at the definition, it says that L, it should be A to the I, B to the J, C to the K, where I equals J or C equals, or J equals K. And this word, AA, BB, CC, fulfills that condition. So it could be that the student might have mixed up the definition of or and exclusive or and just written the test wrongly, which is what I suspect this is. So if we move this to check derive and run it, it's all good. So now imagine if you went through this entire debugging process, even with the visualization, without visualizing the invariant predicates. It would have taken much longer to find where the bugs are, and even if the bug is complicated to debug, or even if you need a complete redesign, you significantly cut down on the debugging time by being able to just glance over the derivation tree, find the bottommost red node, and start from there. So this concludes the demo, and let's see if I'm doing this right. Okay. 1 second. This. Okay. Yeah. So now that the students have debugged their invariants and their grammar is working, they can actually step more confidently into the proof, knowing that their grammar works and after having validated it. So we don't want students to go into the proof trying to prove that a grammar that's not even correct works. And another thing that we find invariant predicates and invariant visualization useful for is the fact that in the proof, students can just reason about the grammar in terms of its invariance. So it makes the proof very short and simple to write.
In order to determine the effectiveness of this new tool, we ran a formative empirical study. There were 8 students that participated, and they rated statements on a Likert scale. And a quick note for the following graphs you're about to see. The reason why there are no 1 and 2 bars is because none of the students actually answered with a 1 or 2 or tended to disagree with any of the statements. So for the first set of statements, we asked them about the visualization generally. And we asked them to rate the following statements: if it helped them understand how the words are derived, if it preserved the history of the derivation, if it helped them understand how words are produced, applied non-deterministically, and if it was useful for debugging the grammars. And here, for all of the questions, the overwhelming majority of students tended to agree, answering with either a 4 or a 5. In regards to the research questions, for the first research question, whether it helps students better understand word derivation, we believe that it does due to the responses to statements 1, 2, and 3 here. Their perception was the response to question 1, and they perceive that it does help them. And in regards to statements 2 and 3, we think that this gives us context as to why it helps them. In regards to the second research question, whether it helps them understand nondeterminism, we believe that the responses to question 3 imply that it is indeed helping them. And finally, in regards to question 4, whether it helps them in the debugging process, again, we believe the responses to the fourth statement imply that it does help them with debugging. The next set of statements were in regards to the invariant visualization. And so we asked them if they felt that the visualization of the invariants was useful, clear, useful for developing correctness proofs, and useful for debugging their grammars. And once again, for all of the questions, the overwhelming majority of students answered with either a 4 or a 5, tending to agree. In regards to the first research question, whether it helped them better understand word derivation, we believe that it does due to their responses to the first 3 statements. And here, because they responded positively, we believe that they have a strong understanding of the invariants of their grammar. And because they have a strong understanding of the invariants, that means they have an understanding of the syntactic categories, and thus understand word derivation and how is an exercise of divide and conquer. In regards to the third research question, whether it helps them develop their correctness proofs, we believe the responses to statement 3 imply that it is helping them. And in regards to the fourth research question, whether it helps them with the grammar debugging process, we believe that the responses to statement 4 also imply that it is helping them in this regard.
So for future work, for related work, one of the more notable tools for visualizing context-free grammars is JFlap. So in JFlap, students can create context-free grammars and expand the derivation tree by clicking on the non-terminal nodes. But in JFlap, the context-free grammar only fits within the visualization frame. So once you're dealing with a larger word and a larger derivation tree, it compresses into the frame, making it very difficult to read. And to our knowledge, we are the first ones to actually introduce invariant visualization in a tool like this. JFlap does not provide that option. For future work, we want to conduct more in-depth studies to answer the questions why students find the visualization and invariant visualization useful. We want to extend the work to support unrestricted grammars and extend the work to use the LL1 and LLR parsing, as well as visualize the CYK algorithm. And if you'd like to adapt our approach in your classroom, or you're just interested in any parts of it, I would encourage you to check out this book. And finally, to outline our contributions, we present a novel visualization tool for context-free grammars. It is already integrated into FSM, and it is a stepwise construction of the derivation tree with colors to indicate the current derivation step and informative messages to provide any additional context on the tree. Finally, our second contribution is a visual validation of invariants, where users can actually visualize whether their invariants hold, and we find it useful for faster debugging. The QR code is FSM on GitHub, and I invite you to check it out. Thank you for your attention. We are open to any questions.
Very nice work. I especially like the way you handled the invariant handling. I think that could be very useful. What I'm wondering about is perhaps applying this in reverse, which is to help people track down parsing errors with their own code, rather than generating grammars and debugging grammars, rather than debugging the parse errors themselves. Are your thoughts on how this could be applied there?
We've actually been looking into doing it in a more bottom-up way to achieve something like this. So it's very, very future work, but it is something that we've considered, yes.
Any more questions?
So there are a couple of phenomenons that you can sometimes notice in Likert scale-based evaluation. One of them is the I like pressing for student, and the other one is the I like pleasing my teacher student. I'm wondering if you had, when you're assessing your questions, given any consideration to asking them in a negative way, like, I believe that I could understand better without the tool, or something like that.
So we actually have a slide prepared just in case. This was definitely a limitation of our study, the fact that the statements were phrased in a positive manner. We are planning on conducting more qualitative and quantitative studies to kind of address that. So.
But I guess when you were looking at your students' answers, did you see any students who seemed like the I like to answer for student, or did they all seem, like they were varying their responses in a way that suggested they were taking it seriously?
Anecdotally, I don't think anyone is too pleased to please the teacher, at least from our batch. When it comes to When it comes to kind of just pressing whatever, we've had a small enough class where anecdotally, it's been emphasized that we do appreciate kind of honesty, and it's been practiced before. We've had studies where we've gotten lower responses, so we've known, like, just experientially based on our previous studies, that that they can be objective if they like to.
Great, so maybe the standard criticism doesn't apply as much as usual.
Do we have any more questions? So if you go back to your future work slide, and you mentioned this supporting of unrestricted grammars, what do you imagine happening there? Any specific problems that might arise?
So this is already done. I'm pretty sure this is published at this point when they were making. Right. But so the problem that we have with unrestricted grammars is the fact that the derivation tree, if we're visualizing it this way, not only expands but can shrink. And we presented this last year at the student research competition here. So what we've done is we've created these special nodes that were these hexagon nodes that preserve the history of the derivation tree by showing what used to be in place of the substituted group of terminals and non-terminals. And additionally, because the tree kind of gets all over the place, we've pushed the yield all the way, or we use the special node grouping to push the yield all the way to the bottom of the tree so it's aligned, and at any point the user has kind of the idea of what the yield is and can also observe the derivation tree. Those are the main challenges. So how to design that to not make it ugly, and to still preserve the history in like an effective way. So yeah, do you have anything to add?
I will say, because we're preserving the history using those hexagon nodes, it's no longer a derivation tree, but actually a derivation graph. It just looks like a derivation tree due to the way that we're formatting it with the yield nodes all at the bottom.
Thank you. Any more questions? If not, then let's thank the speakers. Thank you.